Welcome to Math 201, the lesson on sections 3.9, linear approximation, and 3.10, the mean value theorem. Just a reminder how to find the equation of a line. There are two common forms, slope-intercept form, y equals mx plus b, and point-slope form, y minus y naught equals m times x minus x naught. In both of these formats, m represents the slope of the line. In slope-intercept form, b is the y-intercept. And in point-slope form, x naught comma y naught is any point on the line. So just to review, let's find an equation of the line that passes through the points 2, 2, and 4, 3. Okay, I'm going to do it two ways. I'm going to use both forms of the equation of a line in case some of you are familiar with one and not the other. Okay, so I'm going to start, both of them, I need the slope. So I'm going to start by calculating the slope. So that's the change in y over the change in x, which is 3 minus 2 over 4 minus 2, which is a half. And then I'm going to use y equals mx plus b as the format of my line. And I have y equals 1/2 x plus b. Because I now know the slope is a half, I put that in for m. And then to figure out the b, I can use either of the 2 points that I was given. You plug in the x coordinate for x and the y coordinate for y, and then you can solve for b. So we're going to have 3 equals 1/2 times 4 plus b. So 3 equals 2 plus b, so b is 1. And my final equation of the line is y equals 1/2 x plus 1. Okay, and then the other method would be to use point slope form, y minus y naught equals m times x minus x naught. And I'm just going to plop in either point again for x naught, y naught. I'm going to use this one for this example. So I'm going to have y minus 3 equals 1/2 times x minus 4. And you can just circle that. That is an equation for the line. It said to find an equation, not a particular one. But if you like this method, you can also put it into mx plus b format by distributing the 1/2 and solving for y. So we're going to get y minus 3 equals 1/2 x minus 2. Just distribute the 1/2 and then add 3 to both sides, and you get y equals 1/2 x plus 1. Same equation as the other method. Okay, so the reason we reviewed finding the equation of a line is because we are going to be finding equations of lines today, tangent lines to be specific. So I am going to look at the function f of x equals the square root of 1 plus x, and I want to build a linear function, we're going to name it L of x, that behaves similarly to f when I'm near 0. So I want to find the tangent line approximation for f of x equals radical 1 plus x at x equals 0. And I've drawn a picture. So I have radical 1 plus x graphed, and I drew the line tangent to that curve at x equals 0. And you can see that when I'm near x equals 0, you can't even tell the difference between the function f and the line L. So I'm just trying to find the equation of this line. So I'm going to start by finding um, the slope and a point. So to find the equation of a line, you need the slope and you need a point. So I have a point on the line. This point is on the line, the point of tangency. It's on the line and it's also on the curve f. So my point is the point that's on the line and on the curve. So it's at x equals 0, comma f of 0. Okay. It's on L because it's the point of tangency, but it's also on F because it's the point of tangency. Okay, so this is 0, comma 1, just plugging a 0 into the function f. And then my slope, the slope of the tangent line is the derivative. So my slope is f prime of 0. And so I just got to calculate f prime of x. So f of x is 1 plus x to the 1 half, which makes f prime of x 1 half 1 plus x to the negative 1 half. And f prime of 0 would be 1 half. So now I have a point and I have the slope. I can find the equation of the line. So I'm going to use y minus y0 equals m times x minus x0. And this is my x0, y0. So I have y minus 1 equals m, which is a half times x minus 0. And that comes out to y equals 1 half x plus 1. And we're going to name that L for line. L of x equals 1 half x plus 1. Let's use our linear approximation to estimate radical 2. Coming up with an estimation for radical 2 without a calculator is a hard task. So this is something we could do. If I wanted to know f of 2, right? That would be the square root of 1 plus 1, which is square root 2. Okay. So if you plug a 2 into the function f, it's going to, oh, sorry, no. You have to plug a 1 into the function f to get square root 2. If I plug a 1 in for x, becomes square root 1 plus 1, which is radical 2. So if I plug a 1 into the function f, I get radical 2. And I know that when I'm near 0, L is a pretty good approximation for f. So I'd like to know f of 1. And it's hard to calculate square root 2. So instead, I'm going to calculate L of 1 because the line should be pretty good approximation for f as long as I'm not too far from 0. And L of 1 is 1 half times 1 plus 1, which is 1.5. And if you type square root 2 into your calculator, you get 1.414. Okay, so our line did a pretty decent job of estimating the square root of 2 to be about 1.5. Is our approximation an overestimate or an underestimate? Okay, well, based on what we got from our calculator, we know it's an overestimate. But also think about our picture. I used the line to come up with a value for f, an approximate value for f at the x value of 1. So this is f, this is L. And so I wanted to know a value for f at x equals 1, but instead I plugged into the function L. And you can see that L is above the value of f at x equals 1. So this is an overestimate. And that happens because f is concave down. So the tangent line lies above the graph. Warning, the tangent line is only a good approximation if you're near the point of tangency. Okay, you've reached your activity for section 3.9. Pause the video, work through these problems, come back and watch the video when you're done. Okay, number 1, we're going to let f of x equal sine of x, and we're supposed to sketch the graph on the axes provided. So sine of x, it starts at 0, 0 halfway through its period. Oh, this is only going to pi. Okay. And looks like that. Okay, so it's 0 when it starts, 0 halfway through its period, and it would hit 0 again at 2 pi if we did a full period, but I'm only graphing this from 0 to pi. So it's 0 and 0, and it hits a max halfway between. So do my best to kind of graph this with a smooth curve. Oh, that was terrible. Oh well. Okay, now I'm supposed to calculate f of 4 and f prime of 4. So if f of x is sine of x, then f of pi over 4 would be the sine of pi over 4. And I'm imagining the unit circle, and the sine is root 2 over 2. And then f prime of x, do that over here, f prime of x would be cosine x because the derivative of sine is cosine. So f prime of pi over 4 is the cosine of pi over 4. And again, I'm looking at the unit circle. Pi over 4 is 45 degrees. That's also root 2 over 2. Okay, so we want to use that information to find the tangent line approximation for f at x equals pi over 4. And we want to carefully sketch our tangent line on the same axes. Okay, so I have a point that is pi over 4 comma f of pi over 4, which was root 2 over 2. And I have a slope, which is f prime of pi over 4, which was root 2 over 2. So I have y minus y1 equals m times x minus x1. There we go. And I could solve it for y if I wanted to. Just add the root 2 over 2 to both sides. And I'm going to sketch this. I'm going to grab the graph from the previous slide. All right, so I was trying to graph the tangent line, trying to find the equation of the tangent line at pi over 4. So it looks like I have graphed, I found the equation for this pink line. Okay, D, use your tangent line approximation to estimate the value of f of x at x equals 0.01 plus pi over 4. Okay, so f of 0.01 plus pi over 4. That would be the sine of 0.01 plus pi over 4. That's hard. I don't, there's no place on the unit circle for that angle. So instead, I'm going to use the equation of the line. Okay, and I'm going to plug into y. All right, so I'm going to get root 2 over 2 times x, which is 0.01 plus pi over 4 minus pi over 4 plus root 2 over 2. Okay, so those cancel, and I have root 2 over 2 times 0.01 plus root 2 over 2, which is 1.01 times root 2 over 2. That's the best I'm going to do without a calculator. And is our estimate an overestimate or underestimate? Well, based on my graph, the pink line I drew is above the purple curve. So this is an overestimate. Number 2, one model for the population in millions of the United States is P of t equals 300 times e to the 0.05 to the t minus 15, where t is measured in years since 2000. Find the tangent line approximation to P of t at t equals 15. So we need a point and we need the slope. Okay, our point is going to be at the t value they gave me, 15, comma, p of 15, right? The point on the curve is also on the tangent line because it's the point of tangency. Okay, and then my slope is going to be p prime of 15, right? Because the slope of the tangent line is the derivative of the tangent line, is the derivative of the function. Okay, so my point is going to be 15 comma p of 15. So p of 15, if I plug a 15 in here, Um, 15 minus 15 is 0. E to the 0 is 1, so I just get 300 as the y value. And p prime of 15, I actually have to calculate p prime of t first. Let's do that. So that would be 300 times, because that's just a constant, and I'm going to work on the derivative of e to the stuff. That would be e to the stuff times the derivative of the stuff, which would be 0.05. So that comes out to 15 e to the 0.05 times t minus 15. So p prime of 15, when I plug a 15 in here for t, that's a 0, and I get 15. So I have a point, I've got a point, and I've got a slope, and I should be able to find the equation of the line. So it's going to use y minus y0 equals m times x minus x0. And I have y minus 300 equals 15 times x minus 15. And I can just leave it like that. Or if I want to solve for y so that I can write this in the form L of x equals, it would just be 15 times x minus 15 plus 300. Just move the 300 to the other side. Okay, we want to use our tangent line approximation to estimate the population in 2016. Okay, so I'm looking for P of 16. That's hard. It's actually hard to calculate that number. So instead of plugging into P, I'm going to plug into L, my tangent line approximation that is very close to P as long as T is close to 15. So L of 16 would be 15 times 1 plus 300, which is 315 million people. Assuming that P of T gives the population correctly, is your estimate for the population in 2016 an overestimate or an underestimate? Well, the formula that we were given, P of T, is an exponential growth formula, right? And it was which started in the year 2000, and it's some kind of exponential growth like that. And we found the tangent line approximation at 15. And because an exponential growth curve is concave up, that tells me that my approximation would be an underestimate because the tangent line will lie below a concave up curve. Okay, moving on to section 3.10, we're going to talk about the mean value theorem. The hypothesis of the mean value theorem says that if f is a function which is differentiable on an interval from a to b, then we can conclude that there is at least one number c between a and b such that f prime of c equals f of b minus f of a over b minus a. So let's add some letters to this picture to see if we can understand what it's saying. So we have some function f on the interval a to b. So this green curve, we're going to call this f. And we're saying it's differentiable on the interval a to b, and this is going to be my a, and this is going to be my b. So this is my interval from a to b. The function is differentiable, which just means it's smooth and continuous. Smooth and continuous between a and b. That means that there's some number c between a and b, such that f prime of c, which is the slope of the tangent line, is equal to f of b minus f of a over b minus a, which is the slope of the secant line connecting a and b. Okay, so this point here is b comma f of b, and this point here is a comma f of a. So when I do f of b minus f of a over b minus a, it's calculating the slope of this secant line. So what the theorem guarantees is there's some point in between a and b so that the tangent line is parallel to the secant line. So maybe right here, if I draw a tangent line, it looks like it's parallel to the secant line. So this says there is a tangent line parallel to the secant line. Again, in English, this says that there is some tangent line that's parallel to the secant line between A and B. So this is A, this is B. There is some tangent line, there's some x value between A and B, C, so that when you draw a tangent line there, it's parallel to the secant line. Does the mean value theorem guarantee the existence of this special point C on the graph y equals square root x on the interval from 0 to 4? It does, because square root of x is differentiable from 0 to 4. Smooth and continuous. Because f of x equals square root x is differentiable on the interval 0 to 4. Okay. So if so, what are the special coordinates? Okay, so from 0 to 4, if I put points there and connect them with the secant line, what's the slope of that line? Okay, so this is 4 comma 2, and this is 0 comma 0. So it's going to be 2 minus 0 over 4 minus 0, which is a half. So it says there is a spot somewhere between 0 and 4. There's a C value. So that my tangent line is parallel. And I'm just eyeballing it. I think it might be right here-ish, where I draw the tangent line, and it is parallel to the secant line. If I want to find it exactly, I'm going to take the derivative because the slope of the tangent line is the derivative. So f prime of x is going to be 1/2 x to the negative 1/2. And I want to set that equal to the slope of the secant line 1/2. Okay, so multiply both sides by 2, and I get 1 over square root x equals 1. So square root x equals 1. So x equals 1. There it is. It is, in fact, at x equals 1, this special point.